In this video, we're talking about direction cosines. Direction cosines are a way to represent the components of a vector that's particularly useful in three dimensions. First, we needed to find something called coordinate direction angles. Coordinate direction angles are the angles between a vector and the positive coordinate axes. So you get three coordinate direction angles, one for each coordinate axis. If you have an arbitrary vector and wanted to rotate it through the shortest angle to make it align with the x-axis, that angle would be the x coordinate direction angle, or what I'll call theta x. Likewise for theta y and theta z. And sometimes in some books, instead of theta x, theta y, and theta z, these angles may be called something else like alpha, beta, and gamma. For an arbitrary vector pointing off in 3D space with non-zero x, y, and z components, the coordinate direction angles will not lie in the xy, yz, or xz planes. These angles are also always less than 180 degrees because beyond 180 degrees, and your vector would wrap around to the other side of the coordinate axis, and then you could rotate just in the opposite direction through a smaller angle. So you have to imagine taking your vector and rotating it through the shortest possible angle to line up with the positive coordinate axis. Whatever that angle is, whichever plane you rotate in, that angle will be your coordinate direction angle. So why do we define these coordinate direction angles? Because of the way we've defined these angles, we can get each component of a given vector by multiplying the magnitude of the vector with the cosine of the corresponding coordinate direction angle. This is because the right triangles that are formed by your vector and each coordinate axis will have the component along that coordinate axis as the adjacent side relative to that coordinate direction angle. So basically you form a right triangle. It's some weird plane that's not xy, yz, or xz. And the component along an axis is the adjacent side, so it will always be cosine. It's just that these triangles, because they're in these planes that are at angles, they're difficult to visualize. But getting to write each component in terms of cosine simplifies things once we have these angles, and it has some very nice properties that we'll look at. Rearranging, we can solve for the coordinate direction angles using the magnitude of the vector and the components, just by taking inverse cosine. Writing our vector in terms of the direction cosines gives us this. Notice this looks like we've written our vector as the magnitude times something containing the direction. So magnitude times something, that something must be the direction. So that must mean that this piece on the right is equivalent to a unit vector along the direction of our vector. In this case, the unit vector has x, y, and z components, and the size of these components are given by the direction cosines. Another advantage to using direction cosines is that for angles larger than 90, cosine will automatically put in the negative sign since your vector is more than 90 degrees from a coordinate axis. That component must be negative. So now we can write a unit vector in terms of direction cosines. We also know that the magnitude of a unit vector must be equal to 1. So using the Pythagorean Theorem, we get the following relationship. This means that if we ever know two of the three coordinate direction angles, we can come back to this identity and solve for the third. Okay, so that's a brief rundown of direction cosines. Hopefully you see where they're useful. It makes it very easy to define a unit vector, and these angles are also very easy to define in terms of the magnitude of the vector and its components. So we'll see some examples where we use these in the future. But that's it for this video. I'll see you in the next one.